We are UBC Sturbridge, an engineering design team of a diverse group of students spanning across 7 subteams. Tied together by a dedication to solve structural problems and build bridges, we design a feasible product that connects stakeholders and community for the city of Winnipeg.
Before we begin, we would like to acknowledge that UBC Sturbridge operates on the traditional, ancestral, and unceded territories of the Musqueam people. Winnipeg is known for its local history exhibits, connecting an urban environment with the confluence of the Red and Assiniboine rivers at the heart of the city. These rivers are vital ecological waterways, home to various wildflowers and birds. Additionally, situated along these rivers are trails that attract paddleboarders. To strengthen the integration of the population with the natural world, a steel bridge is proposed to be built spanning the Red River to connect the trails between the Forks and St. Boniface areas. Steel is chosen as the primary material due to its strength, stability, versatility, and commitments to sustainable practices. Furthermore, an aesthetically pleasing bridge design would help preserve the natural and scenic beauty of the Forks and St. Boniface trails.
We developed a 1:10 scale model bridge consisting of 38 members and weighing approximately 190 pounds, with an aggregate deflection of 1 inch under a 2,500 pound dead load.
Our design embodies efficiency and sustainability through minimizing material usage and optimizing constructability. Through Alter and Inspire, we iterated under-truss and over-truss topology models that optimize material usage and placement. Ultimately, an under-truss design was identified to be more constructible and economically feasible.
Due to the piers being asymmetric this year, the optimal model that we selected involves strong lateral members and a wide bottom chord plate that we implemented in our final design. HSS and tube sections were selected as our members due to their ideal lightness to capacity ratio.
S-frame is used to design and iterate a virtual bridge frame. Regularly, loads are split and distributed equally across both spans. However, due to the asymmetric requirements, we simulated plate loading using a virtual mesh. This approach accurately distributed loads based on the differing stiffness of the spans. Accurate analysis allowed us to optimize material use in the shorter span, reducing weight and enhancing sustainability.
This year, with the establishment of the construction subteam, constructability was a major focus in the design of our bridge.
Through practice, our construction leads discovered that removing barges will be an effective way to improve construction economy.
After careful consideration, a 2001 bargeless builder layout was selected, with a construction time of 16 minutes.
As a result, DNA's finalized design included features that will benefit ARC builders during the construction phase. For instance, we strengthened our piers to function as a workbench during time construction. This feature allows for bridge support while our builders assemble other parts of the bridge together.
Our connection designs balance strength and constructability by using 4 primary joint types. The east-west joints are used for connections and compression. It features a taper at the teeth of the connection that provides rotational and bearing resistance. The U-joint, similar to the east-west joints, but it doesn't have the taper. This joint is used for tension members. The plate joints were used for our 2D diagonals in order to add frictional resistance. And finally, our L joints are light capacity joints used for lateral connections.
Using Python, our DNA members developed an application that outputs the ideal joint sizing for every connection.
This code expedited the calculation processes, allowing for more possibilities to be considered. Additionally, an Excel macro script matched section sizes to individual members and provided a corresponding capacity to demand ratio. Using these results, the S-frame model is iterated and refined to optimize stiffness. Finally, spot checks are run with hand calculations to verify accuracy and ensure compliance with design standards.
The drafting subteam acts as a liaison between the DNA subteam's design vision as well as the fabrication subteam's finished product. And because of this year's design complexities, clear communication was the key to our success.
After obtaining the finalized S-frame model, the drafting team designed detailed drawings through AutoCAD, resulting in a full bridge assembly drawing non-stairs to MasterCAD.
A 1-to-1 3D bridge model was then drafted using Autodesk Inventor. Separate parts and assemblies packages were then prepared from the 3D model to assist the fabrication subteam in the bridge assembly process.
The finalized drafting package is then submitted to our fabrication sponsors, who supply our steel parts. This process allows the team to precisely place individual members in the jigs for each assembly, which is then handed off to the fabricators to weld the parts in place. Special thanks is extended to our fabrication sponsors, Renco, Marcon, and Reliable Tube, for their continued support this year.
Furthermore, UBC Steel Bridge has continued its close relationship with Neek Steel, a leading steel fabricator based out of Nanaimo, who graciously provided us with their time and fabrication expertise.
The construction sub-team hosted weekly construction practices to familiarize members from all sub-teams with timed construction rules, constructability concepts, and the use of tools. For design members, this experience provided valuable insight for brainstorming innovations for optimizing construction efficiency. Consistent practice also helped members get to know each other as the year went by and helped build a strong sense of camaraderie and community.
UBC Steel Bridge thrives on innovation, collaboration, and dedication. Our team achievements reflect the hard work and perseverance of our team, who embrace late nights and countless revisions to bring our vision to life. Now, more than ever, we need to build bridges, not just in structure, but in community and resilience.